another hard problem to go through today. I haven't solved it before. Let's see. So we are given an integer array of unique positive integers. So unique positive, and the array will be nums, which is a list of integers. There are nums length nodes, okay, labeled nums0 to nums length minus 1. Nums length minus 1, okay. There is an undirected graph, undirected edge between nums I and nums j if nums I and nums j share a common factor greater than 1. Return the size of the largest connected component on the graph. Okay, integer tests. Let's start with drawing the graph. So let's say we have this graph, 3, 4. What will be the array that it will be representing? Okay, let's also have like 5, 6. So now we have this connected component, two connected components, and the size of the largest connected component will be 3. But let's first check how this graph will be represented as a list, as we were promised. So, okay, let's say that this one is actually 0. So the 0 and 5 share a common factor greater than 1. So let's say 2 is shared between, how do I mark those? 1, 2, 3, 4, 5, right? So here we have 2 and here we have 2 as the common factor, okay? Now also 1 and 2 are sharing the edge, so they can't share the common factor that these two are sharing, because then it would imply that they're also connected. So 3. We will choose here 3. So then 1 and 3 also have common component, and the next one is 5, so it will be 15, and this will be 5. Okay. Now 3 and 4 also have a common component. So let's now choose 7. Or actually, let's choose 11, because no one told us that those will be the smallest possible prime numbers chosen. So 11, and for 3 and 4, we'll have 3 times, okay, 11 here will be 55, right? Here we'll have 11. Okay, so this is one of the representations that we can have for such a graph. Now, we need to find the largest connected component in the graph. So let's think about the solution. Brute force is factorize all numbers. So that would give us something like 15 will be 5x3, 55 will be 5x11. So then we see that okay, then union find algorithm, right? So we have, let's say, 5 and 3. So this means that any node that we find later that has any of these components should point to like a parent. Let's say that we will choose the parent as an index, right? So this will be index, as we had here, 0, 1, 2, 3, 4, 5. Okay, so we are iterating from left to right, and we have all those elements here, and they're like written as a comma, so we are storing those in a set. And then we iterate over those, and we basically create a union find algorithm, the runner union find algorithm. So we iterate over those, and we compare if there already are So for example, we will store something like 2 will be pointing to 0. It's not union find yet. I'm not sure if I can use union find here. Then for 5 we will be choosing 1. Then for 5 we will be choosing 1 and 3. Then for 2 it will be 3. So now at this point we can understand that this will be a connected component. And actually, should we reverse this dictionary? So 3 as a 3 points. Okay, so starting at the beginning, right? 0 points to 2, and 1.25, 3.25. Then we see another 3 that should point to 2, but since that's are both 3, we need to join those two together. So how do we find what to join to? So if we find an element, let's say we are now considering, so all of those were unique until now. So now we finally find an element that we have already seen. So we just create a union find structure where, okay, we have a node, right? So we know that from the beginning. So each node is just pointing to themselves as a parent. And we were iterating over those, and like the zeroth node is just pointing to itself as a parent. First node is pointing to the self as a parent, and then finally for 2, we see we see the number that is already pointing to a different number. So we are storing this, not this, but this we are storing as a dictionary. So we find that 3 is pointing to 5, and we also we assign that we do union find over the current node that we are considering 2, this node that was also pointing to 5. Also, we need to store both things, right? I need to think about this for a moment. Points to 5 and 3.25. So now I see. Sorry, I have messed up here, right? Created the issue for myself. So 5 is pointing to 1, and 3 is pointing to 1. So then we see 3 and we want to point to 2, but it's already pointing to 1. So we say that instead this 2 changes the parent to 1. So 3 pointing to 2 because of 3 already existing. For 2 we instead say that it's pointing to 1. So the parent becomes 1, for example, right? Then we go to 3. And here we have 5 pointing to 3, which we cannot do. We need to update that. Since 5 is already present, we will change the parent here to 1. But we will also add a new element that 11 will be pointing to 3. And now we see 4 and 11 is pointing to 4, so 4 is pointing to 3. And that's where the union find works, right? Like, so it finds the parent of 3. So parent of 3 is 1. And we are doing this. And then finally 5. 5 should be pointing to 2 wants it to point to 5. Oh, sorry. It's not 0 pointing to 2, it's 2 pointing to 0. Oh yeah, actually, so that's what we wanted to have. So 11 is pointing to 3, and now 2 is pointing to 5, but it's already pointing to 0, so 0 becomes an element here. The problem is, what if we have a situation where we first combined 1 and 2, and then we combined 3 and 4, and then we combined 1 and 3. So what if we had something like this, where we, so another scenario, right, where we have this. So no, I want to combine 1, 1, 3, and I want to combine 2, 4, and then 3, 4. So essentially what I'm worried about, right? That's the union find. It should work, but how do we update everything? Yeah, so we will just need to run find. Yeah. In the end, we will just need to run find for each of the elements. So here 0 will be pointing to 0, so it's pointing to itself, and 5 will be pointing to 0, and then it's also pointing to itself. And then here, like even if we are pointing to different elements, let's say that we have decided that it will be 3 and 3, then 3, okay, 3 is not here pointing to itself, let's say it's 1, right? 0, 1, 2, 3, yeah, let's say something like this, right? So it's pointing to 3 and it's pointing to 3, but 3 is pointing to 1, so we will still find the same parent for all of those, and the size of the connector component will be the size of the pointers to the biggest parent. So my solution is all factorization plus creating this dictionary and doing union find. So it will be O of n. Yeah, factorization plus O of n. So creating this dictionary, we are iterating over the whole array, and then we are doing union find, and for each element it will be a small amount of operations. So it's actually bigger than O of n, right? There is something related to Ackermann function in union find, but it's Ackermann function grows even slower than logarithm, if I'm not mistaken, that there is an Ackermann function involved. So eventually it's like pretty much linear. So let's implement this, I guess. What's the biggest size of the node that we have? Up to 10 to the 5th. Yeah. Let me just take the existing function. Let me just get it from ChatGPT. So here is the factorization function that we can use from ChatGPT. If I had to implement it myself, it would have been painful a little. I was just lazy. Okay, so while we that makes sense. So while we need to iterate over possible numbers, while n divided by d is equal to 0. Okay. What's going on? Why are we appending n? Oh. Okay, it makes sense. Also, let me just copy a different solution that does that for us. Okay, so first of all, and by the way, factorization, right? It will be n times n squared, essentially, right? Because there can be up to d factors checked for each number. So it will be of n squared plus of n factors will be equal prime factorization of num for num in nums. Runtime of n space. Okay, so that's the first thing. Then let's also say that n equals length of nums. Parents will be n multiplied by parents will be actually a list of range of n. I don't remember fully the union find implementation. Probably have to fix this after this meeting, but I think we also need to balance the number of elements that we have parents for. So we do find and we continue. And then once we find, we need to do that recursively. Let me, for now, abstract this away again, just as I did with private factorization. So class union find, and then there will be init self, and then there will be self parents, session, where we will be multiplying, okay, list range of n, and self depth, which will be 0 times n. And then there will be def union self and I and j, integer and j, which will be an integer that does return none. And basically after this iteration they are pointing to the same parent. So something like parent I will be equal to self find I, pj will be equal to self find j, and then if depth self depth pi is bigger than self depth of pj, if it's bigger, so it's deeper than this, that means that this needs to be parent for this other side, right? So how do we update the depth? So we say that self parents of j will be equal parent I, self depth So if it's strictly bigger, then we are not increasing the depth, right? But if this is the case, then we do self parents of I is equal to pj, and else there we have the same depth of these two, right? So then we do self depth in pi plus or equal 1, and self parents, yeah. Okay, so this is union. Now define self I, which is an integer, and returns an integer, so it returns the parent. While self parent of I does not equal to y, I equal self find self parent of I, then next I will be self-parent of I, and then and return self-parent of I, right? So what's going on here? We are just iterating. So not while, if this is not, then we are doing recursive call and we find this parent, right? So then we continue. If it's still not the parent, it's still not pointing to itself, we do another recursive call. Once it finally is pointing to itself, we're not doing any more recursive calls, and we return self-parent I or I, which is the same thing. But then we return it to this function here, and it becomes it gets this parent gets updated and gets updated and updated, because it's possible that we need to update the parent, and then it updates for all, like for the whole cycle of steps that we have made. Okay, I haven't implemented union find in like forever, so now finally we have this union find. So UF will be union find of range n, and then for factorized num in factors, for factor in factorized num, we also have a dictionary. So factor to node, which is a dictionary. So if factor not in factor to node, then what do we do? So if it's not there, we update that factor there. So factor in node, factor I, factorize num factors. So factor to node, factor will be I. Else neighbor will be factor to node factor. So then we need to do union find union of I and neighbor, and then counter will be counter for node in UF, for node in range n, cnt of uf find. Oh, are we returning things? Yeah, we're returning parent. uf find node, or let's just call it for I. For uf find I plus equals 1. And then I'm not bothering anymore. Like, yeah, we will probably have, we can also add and log n operation by sorting here, but realistically I don't know that we will have that many unconnected components, but theoretically we can. So return CNT items sorted. CNC items key will be lambda item first. And we need to return the last element, or maybe let's do it minus item, and then we are returning the first element and again the first element, so the initial element. And for this we are returning the key. Oh no, it's easier. We don't need to return the specific component, we just need to do max of CNT values. That was crazy. It also probably doesn't work, but I also don't have much time. How much time have we spent? 37 minutes so far. Let's see. Has no interpret. Parents. Self-parents. Okay. Wow. Wrong answer. I have no idea what's the issue. I'm guessing all of those are connected to each other. Okay, I'm tired and I need to go. So I will spend a bit of time debugging this offline, but even passing 85 cases after coding up all this, except maybe the factorization function, is cool. And I'm pretty sure that my logic is correct, because it doesn't look like there is something wrong here. It's just that my implementation is incorrect somewhere. Yeah, probably something in union find is incorrect. I'll check it offline. Thanks everyone. See you.